Hi, I'm Seong from Seoul National University. I investigated the rupture directivity of small earthquake that occurred in Korean Peninsula between July to August 2021. Figure 1 shows the regional map of southwestern Korea where six earthquakes of local magnitudes between 1.1 and 2.2 took place for about 1 month period. Near the epicenter region, two earthquakes of magnitudes greater than 5 occurred in 1930s. However, the region has been relatively seismically quiet for about centuries. Therefore, the analysis of recent microearthquakes may offer a window to look at the long-term seismicity in the region and gain insights into potential seismic hazard. Owing to increased permanent seismic stations after 2016 magnitude 5.5 Gyeongju earthquake in South Korea, we could use broadband seismometers and accelerometers that densely covered the epicenter region. Moreover, all six earthquakes were recorded with high quality by nearby stations, enabling unprecedented precise analysis of microearthquakes. Six stations with cyan boundaries in Figure 2 are the local stations used for moment tensor inversion of the largest magnitude 2.2 earthquake. We could perform local moment tensor inversion by modeling waveforms of six nearby stations at relatively high frequency bands between 0.3 and 2.5 Hz depending on the stations. Good fit between observed and synthetic waveforms can be clearly observed, despite using simple one-dimensional model developed for South Korea. Inverted mechanism is strikingly faulting with slight oblique component. The preferred focal depth is about 16 kilometers, which is quite deep relative to average earthquake depths in Korean Peninsula. To resolve the nodal plane ambiguity and spatiotemporal evolution of earthquakes, we performed accurate absolute location determination followed by double difference relocation using HypoDD. Estimated location errors are mostly between few meters to few tens of meters, enabling reliable interpretation of relative locations. Imaged lineament were matched with one of the nodal planes from moment tensor inversion. Also, the events seem to show apparent optim migration with time. Figure 5a shows the waveforms of magnitude 2.2 event observed in strike direction and also the opposite strike direction. It is evident that the waveforms recorded in the strike direction have significantly higher frequency content. We thus hypothesized that a long strike rupture directivity for this earthquake. We adopted empirical Green's function technique or EGF technique, in short, to obtain the source time functions of magnitude 2.2 earthquake. We could obtain clear source time functions for various epicentral distances and azimuths with multi-taper method, hence enabling well-constrained rupture directivity inversion for a small earthquake of duration less than 0.1 second. We used source time function stretching method first suggested by Warren and Silver 2006 paper to reduce the subjectivity associated with manual determination of source durations. Figure 5c shows how differential source time function duration can be measured for two different stations by stretching one against the other to best match the overall widths. Figure 6 shows the summary of rupture directivity inversion result. When aligned by azimuths, Visits of source time functions show clear azimuthal variation, but there are some irregularities implying the vertical rupture component. The best fitting rupture parameters indicate slightly upward rupture propagation, almost parallel to slip direction within the uncertainty. Rupture velocity is determined as 0.72 of shear wave velocity and hence is similar to average rupture velocity determined for large and moderate earthquakes. Figure 6b shows the source time functions aligned with respect to the preferred rupture direction and shows that the widths will match the durations theoretically predicted for the unilateral rupture. Figure 6c also shows that observed and predicted stretching factors show good correspondence. Figure 6d shows that trade-off between rupture direction and rupture velocity ratio is quite small. We also manually determined source time function duration at each station to calculate the approximate rupture length. Rupture length is determined as 215 meters, highly consistent with the spatial extent of relocated event cluster, as can be seen in Figure 4D. Our analysis of 2021 Gwangyang earthquake is one of the first attempts to quantitatively resolve the rupture directivity of earthquakes with magnitude less than 3 in stable continental region. Similar analysis will likely lead to better understanding of seismogenesis and rupture properties of small earthquakes in seismically stable regions like Korean Peninsula. Thank you for listening to my poster presentation.